Okay. So during last week's lab, we did a lot. We went through orthogonal projection, where if we have a vector vein and you want to project it onto y, you try to find the component of vein that points in the direction of y, or you will try to find its orthogonal component. So we quickly went through this formula. Um, we tried to understand, or we tried to convert this formula into Python codes. Okay, and then we spoke about the angles between when you're trying to finding angles between two vectors. Okay, and we converted this formula here into some Python codes. Okay, then we we learned about the Gram-Schmidt process, which is also an algorithm. And we said this algorithm will take linearly independent vectors and convert them to orthogonal or orthonormal set of vectors. Okay, so this is a brief of what we did during last week's lab. Okay, and now moving on to week 4. So during last week's lectures, I am assuming you all joined the lectures or you all went through the recording. It is very advisable you do either of that so that you'll be able to understand what is going on during the labs. Okay. So remember I said you would have to um okay, before I move on, please, in case you have any questions or something, you can unmute yourself and let me know. Okay. So this week we'll be looking at matrices and matrix operations. Okay. We have a lot to do, all right, but I believe it's straightforward and we'll be able to understand whatever um would I would explain today. Great. So I am hoping you can all see my slides. Okay. So week 4 lab session, the topic is matrix and matrix operations. Um, so these are some quick learning objectives. By the end of the session, students should be able to represent and manipulate matrix in Python and NumPy, and also understand and compute the transposes, symmetric matrices, perform matrix arithmetic operations, determine image, kernel, rank. These are all things we did during the lectures on Sunday. Okay, so we are whatever we learned on Sunday, we are trying to understand them, or we'll try to compute them with Python codes. Okay, and also try as much as possible to relate them to machine learning. Okay, great. So, introduction to matrix. So you remember during last week's lecture, Seth said a matrix is a rectangular array of numbers, and in machine learning, a matrix is common. Or a matrix is commonly stores a data set with rows representing observations and columns representing features. So what you have to understand from this is that um so in machine learning, when you have a data set, okay, when you have a data set, that is it's usually a comma separated value file, or usually an Excel sheet. Okay. Um and please, can you mute? Thank you. Okay, thank you. So usually when you have a data set, okay, when you have a data set, it is we are saying that its arrangement is in the form of a matrix in the sense that when you take the role of each data set, it represents an observation, okay? And when you take each column, it represents features. So these are like some terms that are being used mostly in the field of machine learning, okay? And the dimension of a matrix, it can be written as M times N, okay? Where M refers to the number of rows and N refers to the number of columns, okay? In case you are confused, rows is like vertical. Sorry, row is horizontal. Sorry, and the column are the vertical. Okay, in case you are confused. So for a matrix A, as a set of row numbers that is m times n, we denote it as ij entry by aij. Okay, so what this means is that you can see over here, you can see a whole matrix over here. So we have capital A is equal to this whole square bracket. So you can see A11. Okay, you can see A12, A1N. And you'll be wondering, like, what are these? What is going on? Like, you know. So over here, this ij you are seeing, you see, you said we denote its ij entry by a ij. Okay, aij. This ij you are seeing over here represents the row. So they are something like indices. If you remember vectors, okay, you remember that indices refers to position. Okay, so if you have a vector, say b is equal to 1 2, okay, so over here we are saying that the indices is the position of element 1. Okay, so what is the position, what is the index of element 1 over here? We say is 0. What is the position of element 2 over here? We say is 1. That is the same ideology we are using for matrix over here. So over here matrix is represented by a ij. Okay, so over here we are saying a, what is the element? Okay, 1 1, meaning it's on row 1 column 1. Do you understand? If we have A12, meaning it is on row 1 column 2. And it makes sense if you look at it, right? It makes sense. If you take A21 here, we are saying that A, or element A, is on row 2 column 1. Okay, it makes sense. If you are confused, we are saying row is those horizontal observation, and columns are vertically. So if you take a 21, you realize that truly A21 is on the second row and it's on the first column. Okay, so that is the whole ideology, or that is the best explanation to give to what I am saying right now. So over here we have a small mini exercise which says that create a small data set, 3 observations, 2 features, as a Python list of lists. If we say a list of lists, a list, so if you say a list of lists, it's like having a list, and inside that list there's a list. Okay, so a list of lists is you have a list as a whole, then inside the various elements of the list is a list. Okay, you understand as we move on to the subsequent sections. So the mini exercise says create a small data set of 3 observations and 2 features as a Python list of lists. and as a NumPy array. Okay, so great. So over here, you remember we said observations means rows, and features means columns. So ideally, they are just telling us to create a data set or a matrix that has 3 rows and two columns. Okay, so 3 by 2, and that is what you see over here. So over here, say my colleague decided to define that data set or call that data set houses. So they decided to give a name to that data set called houses. And um, these are the various observations and features. Okay. So over here, we said that, so if you want to represent a matrix, remember we said a vector is a Python list. Okay. So if you want to represent a matrix is a Python list of lists. That is a list whose elements are also lists. A vector, if you pick a vector, say v is equal to 1, 2. If you pick a vector, say v is equal to 1, 2, its elements are 1, 2. Okay, it means its elements are integers. But for a matrix, we are saying that its elements are not integers, but its elements are rather lists. That is what we are trying to say. Okay, so if we take this example over here, we are trying to create a small data set that has 3 observations, that is 3 rows, and 2 features, that is 2 columns, as a Python list of lists, that is a matrix. Okay, great. So if you take this example over here, this is a Python list of lists. Okay, in case you are confused, remember that to define a list, okay, we define it with 2 square brackets, as this I've highlighted over here. You define it like this, and each element is separated by a comma, as you see over here. Each element is separated by a comma, and this itself is one list. This is another list. This is another list. Okay, so we have 3 different lists inside the main list. Okay, and that's why we call it a list of lists, and we classify it as a matrix. Okay, I hope you understand me up to this point. Great. So if you take this alone, we call it an observation. So this is the first observation, or this is the first row, this is the second row, this is the third row. Okay. So it's like you are trying to stack um rows onto each other. Okay, you are trying to stack rows onto each other. I hope you get me when I say stack rows onto each other. Okay, and this becomes one whole column. This becomes a column. So 1,500, 1,200, 1,800 becomes a column. Or we can say this becomes one feature. Then 3, 2, and 4 becomes another feature or another column. I hope you get me up to this point. Okay. So if we print it, you can see a pure Python list of lists. Okay. And this one is NumPy. Remember we said NumPy is a Python library where someone has defined his own functions, methods, on how to compute I mean Python easily. Okay. So this is a Python library. Okay. So you can either make use of the pure Python computation we've done above here, or you can make use.
Hello.
Yeah, hello.
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 Yeah, please. I can't see your screen.
Really?
Yes.
Oh, I'm so sorry. Oh, wow.
So if you please rectify it.
Please, can you see it now?
No.
You can still not see it. Okay. So So sorry. All this while I thought I was sharing my screen. So I was talking about matrix. Okay, and we said matrix is a rectangular array of numbers, and in machine learning, matrix stores data sets with rows representing observations and columns representing your features. Okay, and to grab or to get the dimension of a matrix, we we it is written as m times n, which is rows times columns. Okay, and I also said that we denote it as ij, so entry by aij. What I was trying to say was that if you take a matrix like this, if you take a matrix of this sort, that is matrix A is equal to square bracket of small a and 1 1, we mean that it is on the first row and it's on the first column. And ideally, it makes sense because truly it's on the first row. And I tried to say that in case you are confused, rows are like horizontal, okay, and columns are vertically. So you look at things horizontally and you look at things vertically. Okay, so if you take this example over here, A21, okay, I was saying that it means A is on row 2, column 1. And ideally, it makes sense because it's on the second row and it's on the first column. Okay. Then we have a mini exercise here that said create a small data set with 3 observations and 2 features. And remember, I said observations in machine learning means rows and features means columns. So we could have just said 3 rows, two columns. Okay. And I also said just like how vectors represent a Python list, matrices represent a Python list of lists. And I was also saying that if I say list of lists, it means we have a whole list and its elements are also lists separated by a comma. So I gave an instance where supposing we have vector 1 2, its elements or the elements of the vector is 1 and 2, right? But for a matrix, its elements will be a list separated two will be two lists separated by a comma. Okay, so this over here is a matrix, this over here is a matrix, and this over here is a vector. Okay, that's what I was trying to say. Great. Then over here I was saying my colleague defined the data set or the small data set we were supposed to create as um we're supposed to create as houses. Okay, they named the data set houses. And I was also saying that, so over here, this is truly a list of lists because if you look at what I've highlighted right now, these two square brackets, this one and this one, that's what defines a list. And each element, that is this one, and this one, are all separated by a comma. And this element is a list, this element is a list, and this makes it a list of lists, hence a matrix. Okay, great. So I also said that if you pick just this, if we are looking at things horizontally, this is your first observation or your first row. This is your second row, and this is your third row. Okay, and if you are looking at things vertically, if you look at starting from 1500, 1200, and 1800, that is your first column. And if you are looking at things vertically, looking at 3, 2, and 4, that is your second column. Okay, so once you, and I also said NumPy is a Python library. Library consists of functions, methods, parameters that have been defined by someone else, which can be imported into Python and be used easily. NumPy or some Python libraries make life easier instead of you typing long lines of codes. Okay, great. So that is that for this place. Great. So now we'll move on to and please, do you understand me up to this point? Were you able to see my screen? You can type it in the chat. I want to know if everyone is following me so that I don't talk plenty again. Please, are you able to follow what I said? Were you able to see my screen as well? Okay. Okay. Sefianu said he was able to see it. Joshua, what about you? Ryan, what about you? Shey, what about you? Have you been able to follow me up to this point?
Yes, I can.
Okay. Yes, please. Okay. Now let's move on to the second concept. So the second concept is the matrix addition. Okay. The second concept is the matrix addition. So matrix addition extends vector element wise. So if you remember element wise addition. Okay. So two matrices A, B of the same size, very critical, same size, they must be of the same size, can be added to produce C, where Cij is equal to Aij plus Bij. Okay. So you remember over here, if you take element, if you take this matrix A, element A, 1, 1, meaning your I is 1, your J is also 1, which also means your element is on the first row and it's also on the first column. That is the same ideology we are using over here. We are saying that two matrices A and B of the same size can be added to produce C, where Cij and Aij plus Bij. So where Cij is equal to Aij plus Bij. Okay, so if you have a whole matrix that consists of a whole range or a wide range of elements. So we are saying that say I is 1, your J is 1. Okay, we are saying that for you to be able to compute C, for you to be able to compute the value of C, or for you to be able to compute C at row 1 and column 1, you will have to get A at row 1 column 1 plus B at row 1 column 1. Okay, you have to grab both of them to be able to do that calculation. That is what we mean by element wise addition. Okay, that is it for this. So this is useful, for example, when trying to combine two data sets. So remember I said machine learning, if we talk about data sets, it's just about matrices. Okay, when we talk about data sets, it's just about matrices. So this whole idea helps you to combine two data sets of the same shape. Makes sense, right? So if you have two matrices A, B, and you want to add it, it has to be of the same shape. Why? Because we are doing element wise addition. If it's not of the same shape, and I don't know, it might not really work. Okay, so the condition is it must be of the same shape, and that is the same thing for machine learning. Once you have your data set and you want to add it to another data set, it must be of the same shape, depending on how you're adding it though. Okay, great. So we have a simple equation here. So A is equal to A plus B. We've already said that. Cij, which is the element of C. Okay, Cij is element of C at row I and column J. Okay, same for A plus B. Great. So there's a mini exercise here which says that compute A plus B by hand for matrices below and verify both implementation. So we have something here. Okay, it's quite it may be quite a lot for you, but I'll try as much as possible to break things down. Great. Hmm. Let me increase the font. Okay. So we have a matrix over here. Remember we said a matrix is a Python list of lists. So we have a whole list and okay, each element is another list. Okay, great. So this is kind of related to vectors, just that vectors, the elements are not what? The elements are not lists. The elements are actual numbers or floats or something. You get it? Great. So we have two matrices defined over here. So this is one row, this is another row. Okay. So you might as well just do it like this so that you're not confused yourself. Okay, great. Uh-huh. So it becomes like this. Remember I said it's like you are stacking rows on rows. Okay. So this over here is literally you writing 1 3 2 4. Okay. So you could have just written it like this so that you do not confuse yourself. Okay. So let me take it back to how it was. Mm, Okay, so we have B is equal to this. Okay, so over here there's a small comment that says that A underscore py a list of lists. You said it's like a small 2 by 2 matrix, right? So 2 rows, 2 columns, like how I represented it earlier. And if you want to grab A and underscore py 0, it is 1 2. Makes sense, right? This is, you are just comparing it to vectors. If you have two elements 1 2 and you want to grab the position of each element, okay, that is the same ideology we are doing here. That's the same thing we are doing here. Okay, so the 0 over here is the index position. Okay, and this is position 0. If it was to be a vector, all of this wouldn't have been a list. It would have been something like this, just 2. Okay, this would have been something like this, just 1. Okay, but this is a matrix, so that's what makes it different. Okay, that's what makes it different. So this is one element, and we are saying that it's having, or it's in the position of 0. Remember we said Python, when it comes to Python, position and indices starts from 0. Okay, you remember that? Great. So that is exactly what we are doing here. And A underscore py1 is what? Is 2, sorry, is 3 4, because indeed that is the position 1. Okay, same for B underscore py. So now we are saying that all of this whole expression is trying to do element wise addition. It's trying to add the matrix A and the matrix B. Okay, so I did some I, I broke things down for us to easily understand what is happening. So this is like a simple code explanation for you to get what is going on. Okay, so it says that this line is a nested list comprehension, and it builds on the sum of the sum matrix of C is equal to A plus B. So I'll unpack it step by step. So then we have the outer loop which says for I in range len of A underscore py, which is this for I. Remember what I said? I over here represent position. Range, you know what range means. And len is trying to grab like your dimension. Okay, that is what it's trying to do. So over here, you remember len of a underscore py is equal to 2 since A has two rows. So then since it has two rows, we are saying range of len what A underscore py, which is also the same as range of 2, right? Because len of A underscore py is 2. So it's the same as saying range of 2. And this means what? So I is equal to either 0 or 1. Okay, that is the meaning of this expression. It says for I in range len of a underscore py, which means for I in range 2. Exactly that. Okay, so range of 2 is what? 0 and 1. That is what we mean by range. Okay, so ideally the number we are considering is not involved. Okay, so it should have, I mean, usually you'll be confused, whereas you could say the range is 0, 1, 2, okay. But this case, 2 is not involved. So the range of 2 becomes what? 0 and 1. And that is what we mean by for I in range of that, okay. So when you take I is equal to 0, what happens? When you take I is equal to 1, what happens? That is the meaning of that part. And then we have another loop. We have another loop, okay. So like all this, so this is a list comprehension, and we are saying it's a nested list comprehension. So this is one list comprehension. This, what I've highlighted is one list comprehension, okay, and it's inside another list comprehension. This whole thing is another list comprehension. That's what makes it nested. Okay, great. Then we have the inner loop. That is what? For j in range of len a underscore py, what is it trying to do? It's trying to grab the position of 0. Okay, remember we did this over here where we said a underscore py square bracket 0 is 1 2, right? So that is what it's also trying to do here. So you remember that when we say len, we are talking about dimension. Okay, so if you say dimension of this, the dimension of element 1 2, what is it? It's 2, right? Because its elements are 2, right? Great. So that is you, and then so you understand why this gave you this means, why the answer for this is 2. Okay, because len of a underscore py grabbing the position of 0, okay, is equal to 2 since each row has 2 columns, right? So it means that j is also equal to what? 0 and 1, because we said range of len a underscore py grabbing the position of 0 is equal to 2, meaning range of 2 is what? Right? So it means we are considering two numbers when it comes to the range of 2, that is 0 and 1. So we are saying j can take up position of either j can be positioned either 0 or position 1. And when j is 0 or when j is 1, what happens? Okay. Then we have another loop over here, which says we have this um small expression over here. Okay, this small expression over here that is trying to do the element wise addition. So after doing all these, when your i is 1, sorry, when your I is 0 and your j is also equal to 0, what happens? Okay, so I'm coming. Let's see if we can um, use this to do an example right now. Okay, so this example over here is saying that what if I is 0 and j is 0? Then it takes your APY, which is a matrix. It goes to check the position of a particular row and the position of a particular column. Okay, it does the same for this one, checking the position of a particular row and the position of a particular column. And because it's element wise addition, okay, it tries to add each element. So if you take A, or if you take element A as the position of 0, if you take element A as so if you take element A at a position, okay, where the row is 0 and the column is also 0, what is there or which number is there, okay. And if you take B, where the position, okay, of the row is 0 and the position of the column is also 0, what number is there? And all this, we are saying this expression gives you another expression called CPY what IJ. So it gives you an expression where C underscore PY what 0 0, meaning position row position 0, column position 0. Okay, great. So when you run it, that is what it's trying to do over here. So this has given you the answer. Then we have NumPy, okay, which tries to represent it like ideally as a matrix. Okay, so NumPy tries to arrange it like a matrix. Okay, it stacks the columns for you. Okay, that is why sometimes people prefer to use NumPy as compared to just typing the whole Python list, because sometimes it can be confusing. Sorry. Great. Then the next concept is scalar multiplication. The next concept is scalar multiplication. So this scalar multiplication is just like what we did with vectors. Okay, just like what we did with vectors earlier, where if you have a scalar multiplying a vector, the scalar multiplies each element. Okay, the scalar tries to multiply each element of each of the vector. That is the same thing for this. The the scalar tries to multiply each element of the matrix or each list of the Python list of lists. Okay, so we said that multiplying a matrix by a scalar scales every entry. It is true. If we say scales, we are just saying it increases by a factor of something, okay, or it changes the number by a factor of something. And it says think of it as adjusting the magnitude of each feature uniformly and analogous to changing the brightness of an entire image. Okay, that is what we mean by scaling. Okay, great. So we have a simple equation here. Say B is equal to CA, where C is the scalar and A is the matrix. B is also a matrix. But next to it, you see Bij and Caij. And these refers to the various elements inside each matrix. So we are saying that B Bij is referring to some elements at row I and column J. And you see the scalar doesn't change because it is this the scalar that is what we are using to cause that effect or cause that change to the matrix. So the scalar still remains the same. So we are saying that if we have just like how if you have a vector, the scalar multiplies each element of the vector. we are saying that if you have a scalar, the scalar also and you are doing scalar multiplication, it means it will multiply each element of the matrix. So that is what this whole expression is trying to mean right here. Okay, so we have a mini exercise here that says scale a matrix by 0.5 and interpret the results in um, an machine learning context. So machine learning, there's something we call feature scaling. And this is the whole concept about it. Getting a feature and having some particular number or some particular scalar and multiplying it by the features, okay, to put them on the same scale, regardless of how huge the number is. Okay, great. So we have a pure Python implementation here, and we have a NumPy implementation here. Okay, so for the pure Python, okay, we are saying that say we give a scalar is equal to 3. So scaled underscore py. So we are trying to say your final your final result after scaling it by a factor of 3. Okay, that is the what the variable is. And this is some nested list comprehension. Remember, I've told you over and over again that during this course it will be making use of Python lists, list comprehension functions most importantly. So if you don't really understand the concept, or if you don't really understand what is happening or what is going on, you should first try to go on the internet, search something, try to understand and know what a Python list and a list comprehension is, as well as a function, okay, to be able to understand everything. So this over here is the list comprehension. So it's just like what we've been doing previously. So this is your scalar, this is an expression, okay. So the scalar gets multiplied to the element. It gets multiplied to the element at position I and position j. I, where I refers to that row number or that row position, and j refers to that row number or j refers to that column position, okay, or index. Great. So that's the same, just like the same ideology I explained above. You grab the lane of a underscore py, you grab the lane of a underscore py 0. Okay, so when j is 0, what happens? When I is also 0, what happens? When j is 1, I is 0, what happens? Okay, these are simple things we do. And then um, we have the NumPy implementation where you just define your array, okay, and you just multiply it by the scalar. So NumPy is kind of easy to work with, okay. NumPy is kind of easy to work with. NumPy gives you that um um matrix arrangement. It arranges it for you. Because if you take a Python list, okay, so if you take something like this is like a Python list of lists. That is how it gets implemented. But NumPy, people sometimes or usually use NumPy because it gives you that matrix arrangement. It arranges it for you. It stacks the rows for you. Okay, so you are able to see and like you're able to, I mean, tell that this is really a matrix, without that confusion here or there. Okay, so that is it for this one. Okay, you realize that it's literally the same. It's just the arrangement. It arranges it for you. It also doesn't make use of the comments like a Python list of lists does, but it's literally the same thing. Okay. Um, So we move on to the next concept. That is, we have about two more concepts left. So I want us to break for like 5 minutes. I want us to break for like 5 minutes, then I'll come back and finish up. I'm hoping we'll be able to finish everything up. Okay. Please, can you see my screen? I hope you can see my screen. Can any of you see my screen? Joshua, Ryan, Charlotte, Sefiano, please can you see my screen? Hello. Okay, okay, great. Okay. So let's continue from where we left off. So the next concept is matrix multiplication. Our next concept is matrix multiplication. Okay. So a matrix multiplication, as usual, this is one of the reasons why I advised that you always go over the recording, always go over the lectures, okay, to understand what exactly is happening so that like you will not be missing during the labs. Okay, great. So matrix multiplication composes linear transformations. That is, if a subset of raw numbers m times n and b, that their product c is equal to ab. Okay, so in simple terms, we have this element here, c I j. We have a summation of a I k and b k j. Okay, so I'll explain the codes as we move on so that you understand what the key and all of that signifies. Okay, so remember we said for the addition it has to be of the same size, right? That is not the case for matrix multiplication. Okay, you can have a 2 by 3 and a 3 by 2. Okay, and usually if you want to know what your the outcome of your values are going to be, you look at, but first of all, I remember one thing I was taught way back was that, so if you have a 2 by 3 and a 3 by 2, first you have to check if the column of the one vector and the row of the other vector um have the same number. Okay, ideally have the same number. And if they have the same number, then you grab the row of the first matrix and also the column of the second matrix. Then you so it becomes 2 by 2. Okay, which tells you like what your final or your final matrix, the dimension of your final matrix is going to be like. I don't know if you really understood what I said. So over here, from what I said, or from what we are going to learn, you realize that at the end of the day, your final answer, okay, your final answer should be a 2 by 2 matrix. That's what I'm saying. Great. So we have all these. Okay, I've if you were following everything I said from the very beginning, okay, you'll be able to understand what this This underscore here shouldn't confuse you. Underscore, this underscore here is just a variable. Okay, it shouldn't confuse you. So for I in range this, for j in this, s equal to this. Okay, all these, I assume if you were following everything we were doing um from the very top, you'll be able to understand what exactly is going on. Okay, so there's a simple or a short explanation down here that you can read through to be able to understand what is going on, but I'll quickly go over it for you to be able to follow. Okay, so we have two matrices. Okay, so over here you realize this is one row, this is another row. Okay, so what we have a 2 by 3. Okay, and we have a 3 by 2 matrix. Remember we said remember we said mn, that is rows times columns. And for you to be able to follow what is going on, this is one row, this is another row, or this is one observation, another observation, or this is one element, another element. And if you want to really understand the whole matrix concept, you just consider the fact that you stack one row on top of the other. But you also have to remember that position matters. So if I say you stack one row on top of the other, you don't bring this one first and put this one beneath it, right? Position matters. Okay, that's the same for this. So we have like a short note over here that says understanding matrix multiplication. Understanding matrix multiplication. So this is the heart of matrix multiplication. Let's try to understand what exactly is happening. So for the outer loop, it moves through each row of X. Okay, that is what this code over here is trying to do. Okay, for I in range of that, it moves through each row of X. Middle loop J moves through each column of Y. Okay, just like what is here. If you just remember, if you were following what we were doing above, okay, this should be easy for you to understand. Then, so each ij pair corresponds to the position in the result matrix, right? You agree, right? Great. Then we have an inner loop K, which goes through all the elements in row I of X and also the column J of Y, and it computes their dot products. I hope you are following. So we have an inner loop K. K over here, you'll be wondering what is it? So K is like going through all elements in row I of X and column J of Y, and it computes the dot product of elements that is in row I of X and column J of Y. You remember dot products. If you remember dot product, our previous lessons, you'll be able to compute this. That is what our K is trying to do. Okay. So mathematically, this is this. We've already expressed it above. And this is an example with actual numbers. Okay. So this is a 2 by 3 and a 3 by 2, right? And it's trying to do just that. So we have 1 times 7, 2 times 9, it's just following what we said here. It goes through all elements in row I of X and column J of Y. So this is one row, this is another row. So we are saying that row, let's say row 1, 2, 3 is multiplying column 7, 9, and 11 of B, okay? And it's computing their dot product. If you remember dot product, multiplication of each and every element, okay? And remember what we said, that your final answer should be a 2 by 2, okay? So that is it for matrix multiplication. So this is NumPy. NumPy is literally trying to um, do the same. Usually NumPy, you see, this is one of the reasons why people like using NumPy. Python, when we're trying to do a pure Python code, we have to type all these to define a function. But NumPy, we're able to import it. We're able to define your array or convert your Python list into a NumPy array. Then use the dot dots. Okay, remember, right? So that is it for the matrix modification. That's what it's trying to do. So NumPy is so easy. Just use your dot dot, then you are good to go, right? So a underscore mp2 dot dot that, okay, dot product of each element of x of a and b, right? When you take a, the one row of a and one column of b, and you multiply them, the dot product of the element, okay, that is that. And then we have another concept, okay, another concept which talks about so it's saying special some special matrices, okay, special matrices. Hold on for me. Special matrices. Okay. Please hold on. Okay. So special matrices have a factor that makes them easy to reason about. So we have the identity matrix. We have that acts like one under multiplication. So we are saying that A times I is equal to A and is equal to I times A. You understand later on. Then we have diagonal matrices. The diagonal matrix scale coordinates independently. And we have triangular matrices, which are useful in solving linear systems via forward or back substitution. I don't know if any of you did some math courses, you'll remember forward or back substitution. Okay, so we have wow, time is almost up. So we have equations. I is so this diag over here is just trying to tell you that if you pick a whole matrix and the diagonal is only one, start from one, ends at one, all of them is one, okay, and while the others are zero, okay, it's trying to tell you something. It's trying to tell you that that is an identity matrix, okay. That's it for the diagonal, okay. So we have a mini exercise here. We have a mini exercise here. It says that construct construct a 3 by 3 identity matrix and multiply it by a random matrix and verify the result equals the original matrix. I don't really know. I've gone through the codes alright, but I don't know if it did a specific task. But let's see. Okay, great. Oh, okay. So this is a mini exercise. Doesn't essentially mean it was that. Sorry. So we have zero matrix. So I've commented some should I say some sentences down here for you to really understand. Okay. So we have 0 for underscore. Remember I said underscore is nothing scary. Underscore is like another variable. Some variable we don't really, should I say, care about. Yes, in range 3. Remember, if we say range of 3, we are what are we saying? We are considering numbers 0, 1, and 2. That is range of 3, right? Uh-huh. So so it means you are creating a 3 by 3 matrix filled with zeros. Okay, 0 for this in range this. Okay, you are creating a 3 by 3 matrix filled with zeros, which means, so for your inner loop, so 0 for underscore in range 3, it creates one row, right? Right. So range 3, remember? So 0, 0, 0. Then the outer loop for this in range 3, and it repeats it 3 times. Makes sense, right? So we have 3 rows and we have 3 columns. That is the result down here. Remember I said that usually for a matrix, in order for you not to be confused, it's like you are stacking one row on top of the other. But remember that position matters, so it's not like you can mix things up. Okay, but over here, because everything, like all of them, all the elements are filled with 0, like we might not really care about the position over here, right? Because regardless, even if you change things, it is still 0, 0, 0. That's what I'm trying to say. As compared to if we have maybe 0, 1, 2, and some other numbers, you can't just mix things up. Why? Because position matters. So it's like you are stacking one row on top of the other, taking position into consideration. So I wrote that seems like stacking rows on each other. Cool, right? So when you print it or when you run it, this is your final answer. This is a whole matrix, a Python list of lists. Okay, great. And if you want to convert this into a NumPy array, you just do np.array, then you put in the variable name there, then it changes it into, like, it looks much more like a matrix format where it stacks the rows for you. That is if you want things like that. But ideally, this is the same thing, even before converting it into an array. Okay. And then we have this, that is identity. Okay, we have identity matrix. This too is here. So as usual, if you were following what have been said previously, this is very easy to follow. It says 1. So if position I is equal to position j, so it's saying that if position I is equal to position j, put 1 there, else put 0 for j in range of 3 and for I in range of 3. That is simple. That is basically what this code is trying to do. If I is truly equal to j, put 1 there, else put 0. Okay, that is if you are trying to compute for the identity matrix. And the result over here, I commented the result over here. So you understand why we said in on top here is diag 1111, right? Because the diagonals are just values of 1. Okay, and that's what makes it an identity element, where all the diagonals are 1 and all the others are 0. Okay, so that is basically what this code is trying to do. Easy, right? Great. So over here I've already explained, but let me just read what I wrote here for you. So it says that the identity has ones on its main diagonal where the row index is equal to the column index. Okay, that is what the code tried to do. So the logic for each cell ij. If I is truly equal to j, put 1 there, else put 0. Okay, that is what um this code is trying to do. That is what we are trying to achieve, okay, for the identity matrix. Then we have diagonal. We have diagonal. So over here, that's giving us some diagonals to consider. Remember, identity is 1, 1, 1, 1. Apart from that, it can be any other matrix. So we can truly say an identity matrix is also a diagonal matrix, right? Just that the fact is that instead of different numbers, that for the identity matrix, the diagonal is strictly 1. Okay. But for a diagonal matrix, it's not only 1, it can be 0, it can be 3, it can be other numbers. Okay. And the diagonal and truly the diagonals, while the others are 0. Okay. That is a rule. Right. Great. So this is also another list comprehension. Exactly. Ideally, J, I, these are position, these are indices. This is saying that, okay, so we've defined something over here. We have DAX, which is a list 103. Grab the position. Okay, grab the position of this, grab it. So if I is 0, okay, what element is there? 1, right? If I is 1, what element is there? 0, right? If I is 2, what element is there? 3, right? Okay. So dags of what? So if I is 0, dag of 0. Okay. So 1, if I is truly equal to j. Okay. So it's telling you that, so it's telling you that if I is truly equal to j, put this there, put this there, put the value of this there. And what is the value, right? The value is dark underscore vowels I, which can be either 0, 0, 1, or 2. Why? Because we are considering range 3. Range 3 is from 0, 1 to 2. Okay. So if I is truly equal to j, put this there, else put 0 for j in range 3 and I in range 3. Makes sense, right? Easy. So this should be your result, okay? Where all other parts are 0, but the diagonals are different numbers. So we can say the identity matrix and the diagonal matrix are kind of, you know, similar. The only difference is identity is strictly 1 at the diagonals. Perfect. So what's happening, I've already explained, but let me just read through. You define your diagonal entries, that is 1, 0, and 3. Then for each cell I and j, if I is truly equal to j, place the corresponding diagonal value. Okay, diag underscore vowels I. Remember, if you have the square bracket and some number in there, it's trying to grab the position of that particular list. Okay, else put 0. That is basically what I've explained. Okay, so this is NumPy. NumPy makes life easier. NumPy is saying instead of writing all these, just type np.zeros 3 3, 3 columns, 3 rows. Okay, identity np.I, that is NumPy's own, NumPy's own way of identify identity element. Sorry, identity matrices. Sorry, diagonal is np.diag, but it has some vectors, a, a vector or some list you have to make use of, and that is this over here. That is 1, 0, and 3. Okay, so this is NumPy. Easy peasy. But as usual, you have to really understand the Python code. You have to understand everything happening behind the scenes. Okay, that's why I say NumPy makes life easier. You could have literally just typed this, then you're good to go. But you have to really understand what is happening behind the scenes so that you don't get lost. Okay, so that is it for this part. So we have like two more concepts to go. Let's finish at. Okay, so okay, there's something here. What each function does. So NP dot zeros creates a 3 by 3 matrix of zeros. NP dot I3 creates a 3 by 3 identity matrix. Identity, remember I said identity matrix is the diagonals are strictly one. The numbers are the diagonals are strictly one. You can literally have a 4 by 4, a 5 by 5. All other parts are zero, all other elements are zero, but the diagonals are strictly one. Then we have np.diag, okay, where you have to define what diag is. Diag is like some values at your diagonals. Okay, so it's you can see that np.diag depends strictly on diag underscore vowels. Okay, so depending on the number of diagonals, that is what is really going to determine how your whole diagonal matrix will look like. Okay, so if your diag underscore vowels has like over here, you see it has 3 elements. Okay, if it has like 4 elements, 5 elements, all the parts are zero. So it is that is what is really going to define how your matrix or the dimension of your matrix is going to be like. Okay. Okay, so NumPy is more efficient and cleaner for matrix operations compared to nested list comprehensions, and we've all seen it for ourselves, and we can all testify of the fact that NumPy makes things way easier. Okay, but sometimes you have to understand what is really happening. Okay, so you don't get confused at some point, right? So then we have transpose and we have symmetric matrices. Okay. Great. So the transpose A, should I say A power T? Let me say A power T. Flips rows and columns. Okay. So transpose is where your row is no more a row, but it becomes a column. So there's this kind of swapping. So um if you have elements, let's say if you have elements and the row is sorry, if you have how do I put it, if you have a matrix and the first observation or the first row is 1 2, if you transpose that matrix, the column becomes 1 2. Okay, so like it's no more horizontal, it becomes vertical. Okay, remember we said rows are horizontal and columns are vertical. Okay, that is what transposing does. It changes that horizontal thing or horizontal observation to vertical, or it changes a row to column. It's like there's this swapping. Okay, and I am hoping you understand what I'm saying or what I've been saying so far. That is if you were really following last week's lectures, which I believe strongly you were following. Okay, great. So then that is it for transpose, right? Great. And then we have what something we call a symmetric matrix. And we are saying symmetric is if A is equal to its transpose. You have a matrix A, has rows, it has columns, and if you swap its rows and if you swap its columns, so that is the row which used to be horizontal now becomes vertical. Okay, so for a symmetric matrix, we are saying that the matrix itself and its transpose are the same. Okay, so we have an example over here where this is a matrix. Okay, and to compute its transpose, remember this expression, what this expression is trying to mean. Okay, so we've explained all over and over again. We are saying that a ji for j in range of this. Okay, if we break things down, you'll be able to understand. That is, if you have been following from the very beginning, you'll be able to understand everything I've said so far. Okay, so there's an explanation here that says, let's unpack this nested list comprehension, where len of A is the number of rows, which is 2. Len of A0 is the number of columns, all through to this. Okay. Then we have NumPy doing this. Okay. Symmetric matrix. Say that symmetric matrix satisfies the condition where Sij is equal to Sji. Okay. So in other words, the matrix is mirrored along its main diagonal. Okay. So this, as usual, this over here is trying to explain this particular code, and I believe strongly that once you get the Jupyter notebook, you'll be able to follow everything we've been doing so far. So this is a matrix A, this is its transpose. This is just some colors to know what exactly is happening. Then we have the range, we have the kernel, we have rank, we have nullity. Okay, if you were following last week's lectures, okay, we understood that an image is a column space of a span of its columns. A kernel, that's the null space, is a set of vectors set to 0 by a. Rank is a dimension of that particular image. Nullity is a dimension of that particular kernel. And it says that they satisfy this theorem where rank of a plus the nullity of a is equal to n. Okay, the column space. So these are codes to briefly explain what each um, line is doing. Okay, and that will be all for this week. Okay, we didn't go through all of these during the lecture, so I will not bore you with all these. But that will be all for this week. The following week, or sorry, I mean tomorrow, so we'll take us through matrix inverses. Okay, but other than that, that will be all for today. I know you may have some questions, but the breakout session ended abstractly. So I'll have to end things here. Okay. So that'll be all for today. In case you have any questions, you can text me, you can let me know. But I believe strongly that once you go over the Jupyter notebook, you'll be able to follow everything that has been done so far from lectures till now. Thank you so much for having me, and I hope you do have an amazing week and see you during tomorrow's lectures. Please try as much as possible to learn a Python list, a Python comprehension, a Python function. That is if you're a beginner in Python. And please try as much as possible to join the lectures or watch the recordings before you join the lab so you don't get lost. And please try as much as possible to go over the Jupyter notebooks and also do the assignments. Every single week there's an assignment. So make sure you don't miss the assignments because all of them it will end up affecting your total grades. Okay. So thank you so much for joining my lab and I hope to see you during next week's lab and also see you during tomorrow's lectures. Thank you once again and goodbye.